All right. So remember when I was going on about how like, hey, this can be done with electrochemistry. This thing's gonna show up in electrochemistry. How a pH meter works, electrochemistry. Well, here we are. I know it follows right after. So again, the electrochemistry is going to be a branch of the analytical chemistry. It's going to use obviously electrical measurements to measure chemical systems for an analytical purpose. Analytical purpose typically means that you're going to have to identify or you're going to get a number of some sort with error, right? So remember that there's many different ways that electrochemistry can be implemented. So electricity is electrons, right? And so electrons can obviously drive chemical reactions. The chemical reaction be used to produce electricity because you can just do the reverse. We're talking about redox reactions there, obviously, right? And so you have to understand the redox reactions to understand how electricity is implemented and reacts within chemistry. They're the primary way that electricity is going to be involved in chemistry. Interesting enough, there's actually been some really like crazy breakthroughs lately of using like electricity to cause CO2 to form polymers, and there's been some really wild stuff that's happened in the last like few years with electrochemistry. So I'm just gonna cover the basics. You can cover the more advanced stuff in grad school. Or you're on your own, whichever way. So let's involve the transfer of electrons from one species to another. That's going to be a redox reaction. It's obviously two parts, reduction and oxidation. Oxidation is going to be the loss of electrons. Easy way to remember that is, what does oxygen do to most things? It takes electrons from them, right? Oxidation is taking electrons from it. The alternative way that I typically remember this is reduction is the gain of electrons. When you gain electrons, it's a negative, so that's reduction, right? Literally reduction of the charge. All right. The oxidizing agent is going to take electrons from the species that is oxidized. This is where a lot of people fall apart. Kind of like saying the assassinating or the assassin. That's not the person that dies, right? It's the person that assassinates, isn't it? Oxidizing agent is the one that oxidizes something else, okay? So the oxidizing agent always has to be reduced because it does that to something else. Reducing agent is going to be the one that gives the electrons to the species that is reduced. So that's the one that's oxidized, is the reducing agent. So right here is a summary of that in a graphical format. You see here, this is the oxidizing agent, therefore that's the one that's oxidized, right? See that? And that's the reducing agent, so this one's the one that's reduced. You look over here, they're monoatomics with a charge on them, and so figuring out their oxidation states is super easy, right? Because it's just that charge up there. Iron goes from 3+ to 2+, that means it had to have been reduced, doesn't it? Literally the number was reduced, wasn't it? Cool. Okay. You having any issues with this? Everything coming back from? Okay. Fantastic. All of that was, by the way, just general chemistry, right? We'd actually covered it in general chem. So the electric charge, Q, small q, notice that is the same thing as heat would normally be, small q. I know it's annoying, but it is what it is, right? We just have to deal with it. The SI unit of electrical charge is the coulomb. This is one of the ways you can kind of help yourself remember, is look at your units whenever you're doing these equations, okay? I know that the damn constants are same things as like 3 other things in chemistry, which is a pain in the ass, but the units are different. So that's coulomb, it's a measure of charge. The charge of 1 electron is 1.602 times 10 to the negative 19th coulombs. So 1 mole of electrons would be this right here in charge, which is 9.649 times 10 to the fourth coulombs of charge. That number is actually Faraday's constant. It's the charge of a mole of electrons. So the capital F, Faraday's constant, that was on your sheet I always give you guys for exams, that was a mole of electrons worth of charge. Okay? And that's the actual units of a Faraday's constant, by the way, is literally coulombs per 1 mole of electrons. All right. Current, this is denoted by a capital I. This is the quantity of charge flowing per second. This is the one you've probably seen before because it's the ampere is the unit, or amps. Yeah. Or if you're talking medical field, it would be microamps usually, because a microamp, like 4 microamps, can kill a person. Yeah. You don't need many microamps to kill somebody. Interesting enough, a body can take on infinite charge as long as it doesn't allow the electricity to flow through it. Do you know that? Yeah. There is no known high or low point for charge. You can go well past 10,000 volts of charge, no problem. Tesla actually proved this. He used to have a demo that he'd do, and he would put himself on a charge cage, which is an electrical conducting skeleton that he'd wear under his suit, and lightning bolts would essentially pass through him without hurting him. And then he'd like extend his fingers, and he'd have a lightning rod out in the audience, and he'd like shoot lightning bolts into it from his fingers. But it wasn't from his fingers, it was from the skeleton running along, like an electrical conducting skeleton. And yeah, those things can get hot, and if they're not really great conductors, and harm the person. So you gotta be very careful, don't do that at home. All right, so electrical potential, this is E. You may remember this, potential energy, electromotive force, remember that? And we described it with like the analogy of a waterfall. Okay. So electrical potential, this is the work needed or done when moving electrical charge from one point to another. This is the energy unit, by the way. The SI unit of this is the volt, which is V. By the way, the ampere is typically AMP is actually the one you see more, because A gets used a lot in equations that are related to this, and so you'll see A as a variable in equations that you may end up using alongside this, like activation energy and stuff. Yeah. So most people put AMP, they don't put A for the unit, in case you're curious. By the way, all of these units actually work into each other if you know how to solve them back and forth. They're all related. Like this is a coulomb per second, because it's literally a flow of charge per second, right? That's an amp. There also have workouts that you typically do in like physics 2 that are things where you see that these are all composed of different variations of joules with other units in them, if you're ever curious. So you can actually work them down into the joules components, because this is obviously an energy, right? So it has a measurement in joules. One thing you should keep in mind is that these are different energy levels, but because of how electricity works, this right here is, because of what this unit is, this is not a measurement strictly of joules or kilojoules like that. This is actually a like, you know how we do kilojoules per mole numbers? Okay. And that makes it so it's intensive rather than an extensive value. Remember the difference there? Extensive, it matters how much you have. Intensive, it doesn't matter how much you have. Okay. This is an intensive value. It doesn't matter if you have a drop or if you have an ocean of the thing, it's the same amount of voltage. Does that make sense? Think of it more like a waterfall height. It doesn't matter how long your waterfall is, right? the height still gives the same amount of energy for going over it. Okay? Okay, so remember this is a work, so 1 joule of energy is going to be gained or lost when 1 coulomb of charge moves between points whose potentials differ by 1 volt. Okay? So the easiest way to sort of think about this is that, well, this is work, joules. That's the energy moving something. Volts would be your height of your waterfall. Coulombs would be how much water goes over it. That make sense? It's kind of your weight of the water. Because, the electrons will have very little weight, if any. We're measuring charge. That's what's changing. Does that make sense so far? Okay. So the free energy change of a chemical reaction will be directly related to the voltage that can be generated by the reaction. You'll actually notice, if you've taken biochemistry before this, we actually do this exact same thing. We relate delta G to this point right here, which is the electrical energy, because a lot of those reactions that generate energy in a body is electrochemistry, redox reactions. So this right here is the how that works out. Notice delta G is already a negative number, makes it spontaneous. And so it's negative work, negative E times Q. That can be substituted in for the E times Q right here. There's the E term, this is the Q term. And that's Faraday's constant, that's your moles, that's your voltage. Okay? All right. By the way, we'll get into it. It's interrelated with resistance and watts, if you're curious. We'll get there very soon. So Ohm's law, this states that current is directly proportional to the potential difference across a circuit and inversely proportional to the resistance, which is denoted by a capital R in this case, across the circuit. So the SI unit of resistance is actually the ohm, and it has this symbol right here, which is that omega sort of symbol. Okay. By the way, the water is always denoted for purity as 18 megaohms. So it's literally telling you how resistant it is, because the more ions that are in it, the less resistance it has, right? So if you're ever curious what the hell's going on. Remember that circuits don't have to be a piece of metal, okay? A circuit could be anything. It could be waters with ions in it. It could be, pretty much anything. An ionized trail through the air, that can be a circuit, okay? This is the equation right here. Are you okay with that so far? Fantastic. All right, so power, P, this is the work done over unit time. The SI unit of power is going to be joules per second. This is what we call a watt. You typically see on your power bill is like a kilowatt, kW. And so, yes, that's watt. That's the power, the work done over a unit of time. Please note that this is a kilowatt second, is what they'd call that in the electrical engineering world, the power company world. What they actually put on your bill is a kilowatt hour. It's how many kilowatts you use in an hour, okay? So, you convert the seconds to hours here. Does that make sense? All right. It is something that I always am kind of annoyed about, because a lot of times they don't put kWh, which is kilowatt hour. They'll just put kW and they mean kilowatt hour. They don't mean kilowatt second like what they're putting. Silly bastards. All right. So galvanic cell, this can also be called a voltaic cell. This uses a spontaneous reaction, so your delta G is going to be below 0. to generate electrical energy. Batteries are the most common galvanic cells that you'll probably be thinking of because they're separate enough that you can actually see them as something, that might have science that works on it. But, I mean, this is all sorts of things in your body. This is your ATP acting. This is your man, I'm drawing a blank, please. What's the one that I'm always telling you about in the redox reactions? You know what I'm talking about. It's coenzyme. You know what I'm talking about. Yeah, I'm totally drawing a blank here. It's me coming back from break. Anyways, so right here, this is an overall reaction, a net reaction, or a redox reaction. We have two portions to the redox reaction. We have a reduction and an oxidation. In a battery, we can separate these two into two different cells, and that's why they're referred to as galvanic cells. Please note that they're not always physically separated. Sometimes they're separated by phase, sometimes they're separated by various different properties, okay? But yes, they're separated in some way to make a cell, quote unquote. All right. Okay, so this is the simplest example of a galvanic cell. So what you would have is you'd have electrodes. Typically, they'd be immersed in some solution. Electricity would pass from one electrode to the other, from one cell to the other. The electrodes allow you to pass the electrons without passing the ions. We would also then have a salt bridge right here. This allows you to pass charged ions without passing the ions that are in one side to the other, which would kill the cell, right? And so, for example, here we have a salt bridge that passes potassium and nitrate off to the other side. And that will keep you from building up a charge on one side or another. Okay? These will pass the electrons. Typically, they're made out of the metal, the solid metal for the ion, so the ion can lay out on it and it won't change it too much. But sometimes you make it out of something that's just not reactive, some sort of non-reactive metal, like silver or platinum. Okay? Okay, so this is the anode right here. This is the cathode. The electrode at which the reduction happens is called the cathode. So remember, your reduction is going to be taking on electrons. That means it's going to draw in cations, right? And so it's called the cathode. The side that is losing the electrons, where your oxidation is occurring, that's going to be the anode. So remember, your anode, anions are being drawn in so that they can lose their electrons. Does that make sense? Fantastic. Okay, the salt bridge, many people don't think that a salt bridge, this is a very generalized term, by the way. You don't have to have necessarily a salt, unquote, salt bridge, you know? There are many different options to put in here, like a porous glass layer, etc. Okay? They just needs to allow some sort of charged ions to pass through that won't kill the cell. But in this case, your salt bridge is absolutely vital to a galvanic cell's continuing to run, because if you did not have something to move charge over here, this entire solution would build up a positive charge, wouldn't it? And this one would build up a negative charge. So you have to continuously let potassium come in here and nitrate come into the other side so that you can balance the charge. It would kill the cell if you built up charge, right? Like if you built up positive charge over here, electrons would start being drawn back over, wouldn't it? And you'd end up in equilibrium. And then your delta G would go to 0, right? If you're at equilibrium. Meaning it's not spontaneous anymore and you no longer generate electricity. Guess what that is? It's called a dead battery. So dead batteries are at equilibrium, aren't they? Electrical chemical cells are going to be described by notation that employs two symbols. We have our phase boundary. This could be a physical separation, but most often this is going to be a phase boundary, okay? And it's a single line. The salt bridge will be your double line. So our cell configuration for the previous cell is this right here. CD solid, that's that anode right there, right? Where you're laying out your solid. Phase boundary, CD in its salt form. That's this charged CD, right? This is aqueous, this is dissolved in solution. We then have a salt bridge separating the two. This is then to be AgNO3 aqueous. Again, that's the salt. And then the Ag solid. Please note that you always arrange these by the anode, cathode, and that determines which term goes first here. The anode is going to be, which way is an anode? It can be losing electrons, right? So an oxidation. And so it's going to be arranged as an oxidation, going from the thing with a more negative charge to the thing with the more positive charge. And then you do the reverse for the other. Because the cathode is always going to go from the thing with the more positive charge to the thing with the more negative charge, right? That making more sense? Please note that this is literally phase boundaries, period. So if you have more than one phase boundary, you could have more than one of these lines in. Okay? So if you had like silver electrode with hydrogen gas and then hydrogen in the water, you could have 3 different phases. Okay? It happens, it's possible. No problem. The salt bridge is a generalized term again. Keep that in mind, okay? It's not always necessarily a bridge with salt in it. You can have things where it's like just a porous membrane. Yeah. There's actually multiple different options. Obviously, battery technology has improved considerably. There's a lot more depth to this than I want to go into, right? Again, we're just going to skim on the surface, enough for us to use what we can, okay? If you want to learn more, then this is a great field to go into. All right, so voltage tells us how much work can be done by electrons flowing from one side to the other. The potentiometer, which is also can be called a voltmeter, and oftentimes is, that's how you'd find it like on Amazon. All right. This shows a positive voltage when electrons flow from the anode to the cathode. If electrons flow the other way, it shows a negative voltage. If it shows the other way, by the way, that means you've labeled them wrong. Yeah, right? Okay. So all half reactions are generally written as reductions, and then you would just flip them if you need. Okay? Each half reaction is going to be assigned a standard reduction potential, or an E naught, a standard E, right? Where the standard means that all the activities of all species are unity. Please note that this is a very different definition of standard than you're probably used to at this point, okay? Again, all the activities of all species are unity, okay? All right, so a potentiometer is going to measure the difference in potential of the half cell of interest that you attach to the positive terminal and the potential of the standard hydrogen electrode, which is nicknamed SHE, S-H-E, standard hydrogen electrode, that you've attached to the negative terminal. And that's right here, by the way. See that? This is the components of a standard hydrogen electrode. It literally is using the redox reaction of hydrogen. And so you'll generate hydrogen gas. You'll have a tube here, glass tube, that can take on hydrogen. And then you have a platinum electrode, because obviously hydrogen would not be a nice conductive metal, would it? No, that's not going to work out. This is 0, by the way. This has been arbitrarily assigned the number of 0 for voltage. Okay? So the SHE is your 0 point that you measure everything off of, and it's a relative scale. Just like a Celsius scale would be, right? Where freezing in water is 0. It's arbitrary. We just, decided freezing in water. There we go. Again, arbitrarily decided hydrogen. Because it's easy to make and it's reliable. Again, your voltage is always going to be equal to the positive end minus the negative end, right? Okay. You see that this whole cell right here is the SHE here. All right, so the standard hydrogen electrode, this is the reaction for it. It's, again, the H plus taking on an electron to give you H2, the gas. It has a potential of 0 voltage, which we've, again, arbitrarily assigned to the SHE at 25 degrees Celsius, which is room temperature-ish, right? The SHE, you're okay with me just saying SHE, right? You understand what I'm saying? The SHE is used as a reference point to measure other half-cell potentials because that's our 0 point. So everything that we measure against it is automatically whatever number it gives, right? By the way, that's actually kind of bad form of me to say SHE instead of SHE. I'll be honest, it's a bad habit. If you ever work in this field, most people just say SHE. They don't say SHE or hydrogen or standard electrode. Yeah. Just letting you know, that's actually a terrible habit of mine. Don't do it. Try to not bring that one in. The delta, the E naught, this is going to be measurement of the reaction. In this case, it's positive 0.799 volts. A positive voltage would mean that the electrons flow from the platinum to the silver ion. And so that's actually a reduction. Notice if you place a SHE in here and it flows the opposite way, you're actually getting something that, so this is easier to reduce than hydrogen, right? If it flows the opposite way, it's easier to oxidize than hydrogen. It's the opposite. So these are the ordered standard reduction potentials. Most metals are easier to reduce, harder to oxidize than hydrogen. However, there are ones that are easier to oxidize, right? And that's how we know, remember when you mixed acids with different metals? And some of them gave off hydrogen gas? Well, notice those are all down here. Below hydrogen. The ones that don't typically give off hydrogen gas, if you mix the metal with the H+, the acid, are up here. Okay. All right. So the Nernst equation is going to include 2 terms, one for the driving force of the redox reaction under standard conditions, which is your E naught term, and one that will show the dependence on the reagent concentrations. Remember, we had unity for all our activities for the standard, right? And as we know from Gen Chem 2 and biochemistry, if you've taken it, you remember that we can have something called a concentration cell, right? In fact, that's how life works. We get all the H pluses in one area, and that drives a energy difference, right? That's literally a concentration cell. Okay, or electric eels are also concentration cells. So this would be for this half reaction here. There we have a half reaction. Notice N is the number of electrons here. Please don't get that confused with moles. Okay? I mean, technically it is related to moles, but yeah. Yeah. You know, loosely. I hate the damn way they did some of these symbols. Anyways, so Nernst equation is going to give you your half cell potential E. Again, here's for this half cell reaction. That's equilibrium. The Nernst equation will give you your half cell potential. This will be your Nernst equation. You have your actual value of E, that actual voltage for this half cell. That's going to equal the standard one, which you can find in books. Again, that's just measured against the SHE at room temperature. Minus your constants here, RT. So R times your temperature. Don't forget your R value here. You'd find on tables and such. Typically, you're going to use this one, which is the joules per Kelvin mole. However, if you actually look at that, you can rearrange this to give you it in terms of electrochemical terms, which would be volts times coulombs over Kelvin moles. Hey, isn't that neat? It was always that. See that? All you did is just rearrange these terms, take them apart. Remember, joules was equal to that. Okay. So obviously we have to get rid of coulombs, moles, and Kelvin, right? So we put temperature in Kelvin. Down here we'll do number of electrons, and right here will be the Faraday's constant. By the way, Faraday's constant is coulombs per mole, right? For 1 mole of electrons. This N value is actually your stoichiometric number here. Did you see that? It's the number of electrons. So you're correcting your Faraday for your reaction. Neat, huh? If you have this logically down, then you can actually use, I used to just use this R term right here to figure out the equation. I never memorized the equation. So then you do the natural log of the activity of the product over the reactant to the power of their coefficient. Guess what that term is? It's that reaction quotient. Remember how that reaction quotient shows up in all these corrections? Exactly the same, doesn't it? It's almost always the natural log. If it's not the natural log, then it has that correction factor, right? And then it's always the activity of product to its coefficient power, right? Divided by the activity of the reactant to its quotient power, which is just reaction quotient, isn't it? Cool, huh? So you're starting to see, remember, you probably remember way back when I first started talking about these things, we did like a reaction quotients with equilibriums, we did reaction quotient stuff with energies, and I was like, this is the standard formula that all these damn things follow that same pattern. Yeah, you starting to see that pattern now? Yep, you always have these terms to correct them, right? Anyways, remember that this is the number of electrons in the half reaction. To get the whole reaction, you have to match those numbers, right? So, yeah, you gotta use the one for the half reaction, but keep that in mind. This activities here, this is going to incorporate your concentrations, but don't forget they are activities, okay? So these can change from the ion concentration in the solution, even if they're not involved in the reaction. Anyways, so again, that logarithmic term, that's referred to as the reaction quotient. That's that Q from our equilibrium work. And again, that's the activity of the products over the activity of the reactants, each to their coefficients in power, right? By the way, this term right here, if this is equilibrium, this would be the K. And this would all start to go to 0, right? Well, the delta G would go to 0, okay? Keep in mind, though, the temperature can change things in these. So converting into the base 10 logarithm and inserting t would give you this right here. This is your simplified Nernst equation, which is typically the most useful because you're typically room temperature and you don't really want to use natural log most of the time. Most people prefer a log 10 because you can do things like PE, that sort of stuff. And so this is the form right here. Notice the Faraday's constant, the R, and the temperature have all been summed up here. V is just volts, just units. That okay? Make sense? Fantastic. So these right here, this is the writing a net cell reaction and finding its voltage. These are the steps. So step 1, you'd write the reduction half reactions for both the half cells. You'd find the E naught for each of them. You'd multiply the half reactions so that they'd contain the same number of electrons. So remember though, when you multiply a reaction, you do not multiply its E naught, okay? Because it is an intensive value. It is not extensive, right? So it does not matter how many moles of something you have, that E naught doesn't change. Just like broadening out that waterfall doesn't matter how much broad that waterfall is, the energy coming off it is the same for going down, right? Okay. So step 2, we write a Nernst equation for the right half cell attached to the positive terminal of the potentiometer. This would be your E plus. Step 3 would be writing a Nernst equation for the left half cell attached to the negative terminal of the potentiometer. This would be your E minus. You would then subtract your E minus from your E plus. That would find you your net cell voltage, which is your E with no plus or minus. Then, step 5, you'd write the net cell reaction by subtracting the left half reaction from the right half reaction. And that would give you your overall system, or your net cell reaction, whichever one you want. Okay. By the way, if you mess up on figuring out which is your E plus, E minus, it's not that big of a deal. All you have to do is you've just flipped your values. That means your sign just flips. Okay? And you can kind of figure this out because the positive terminal versus the negative terminal, well, remember that if the electrons are flowing from your anode to your cathode, it should be a what value? Positive, right? If it's negative, that means the electrons are flowing which way? The reverse, right? Yeah. Don't think it's like this very arcane, unknowable stuff, okay? Just try to get comfortable enough that you go, well, this is not unknowable arcane. Galvanic cells produce electricity because they are not at equilibrium. So when a battery reaches 0 volts, the chemicals inside have reached equilibrium and the battery will be dead. Okay? And it does this exponentially, by the way. So, like, once it starts moving off of that center voltage, it's going to be less and less of the chemicals available. Okay? Okay, so at this point, the E will be equal to 0, the overall E, not the E plus or E minus, right? Your overall E would be equal to 0. Your Q would actually be an equilibrium constant, so it would actually be called a K. All right, and so this would be the equations for that. Notice your E naught would equal this simplified version of the Nernst equation with the log of Q is instead K. Okay? Notice these are not 0. See that? So your E naughts are not 0 usually, except for SHE. And they are not 0 for K, typically. Okay? Okay for the K? All right. You can actually rearrange this. K equals 10 to the power of n times E naught divided by this value right here. It's just solving that for the K. You don't really have to memorize it. As long as you got one, you'll be able to get to the others. Okay, did you need help working through this? So this is your equilibrium. We're going to try to find the equilibrium constant for this reaction. So you're going to divide this into two half reactions that you can find in Appendix H, which is your table. Remember, they're all going to be written in reductions, okay? So what you'll do is you'll go, well, this is iron 3 plus, iron 2 plus. So it's iron 3 plus going to iron 2 plus, right? And that's a reduction. Here we have copper and copper 2 plus. That's the reverse. So we're looking for a copper 2 plus going to copper, right? And that would be another reduction. So we'd find that in the table, write it out. Okay. Now we found our 2 on the table, right? This is your plus because it's the reduction. This one right here is your minus cell because it was the other way around, right? We've had to flip it. Okay. So your E plus gets subtracted by your E minus. There's 2 ways you can do this, actually. You can just put a minus for the E minus. You can literally just flip its sign. Or you can do it where you do E plus minus E minus, right? They end up the same thing. I typically just put a negative sign in front of the E minus. So I don't have to remember the equation and blah, blah, blah. I've taken care of it. There we go. Done. And that lets me remember which one's which. And I don't even bother usually putting the minus or plus here. Because I'm lazy. All right. Don't forget you have to get your electrons. The same number of electrons have to pass from one to the other, right? Because one's feeding the other. And so your iron one only has 1 electron in it. And so you're going to have to multiply those by 2. But remember, this is not delta H's or delta G's. Don't multiply that E value, okay? That's the same no matter what number you multiply this by. Doesn't change. So you take that difference between those 2 numbers, you'll get a value of 0.432 volts. Once you have that number, you can start plugging that into the simplified Nernst to find your K value. And so this is the simplified Nernst rearranged. 10 to the power of 2. That's that number of electrons right here. Times the voltage of your cells, so your overall voltage, divided by that constant. You get that number up here. You then take 10 to the power of it, and you'll get this value right here. And that's your K. Did you have any questions? Notice the rules for significant figures in this. So you only have 3 sig figs from these values right here. And when you do this value right here, you can only use 1 for this one because you have 2 sig figs up here in your exponent. Okay? And those are the rules for sig figs for an exponential number. When you put your numbers up here in the exponents. Okay. So you use up 2 of them here, 1 of them will go here. Okay, you have any questions? No? All right, fantastic. So a chemical reaction that occurs within a half cell will reach equilibrium and is to remain at equilibrium. This reaction is not the net cell reaction. Keep that in mind. Is that, again, it is the net cell reaction has to reach equilibrium for the electricity to stop moving. Okay? It is not necessarily one of these reaching equilibrium. It's entirely possible one being in equilibrium will actually still drive it. Okay? All right, so for this figure we just looked at right here, we have half cell reactions. There are these. This is the right-hand cell. This is the left-hand cell. These have come to equilibrium, but neither reaction is part of the net cell reaction. So your redox reaction for the right half cell is this right here. And that still has a voltage there. Your redox reaction for the left-handed cell is this one right here, and that has a different voltage. That's 0 voltage, right? These having different voltages means that electricity will still pass from one to the other. Okay? Is that making sense? You're looking for your overall equilibrium to come to 0, your overall E to come to 0. That would be overall equilibrium. Okay, so our Nernst equation for the net cell reaction, notice that you can set up your Nernst equations for your positive and negative sides in this, so you can plug these in. See, this is the Nernst equation for the positive minus the Nernst equation for the negative. Okay. And then we can just plug in the numbers as needed. In this case, we only don't know H+, so the measured voltage would actually allow us to find H+ in our left-handed cell. What do you think we're kind of looking at? We're kind of looking at a pH meter, aren't we? Yeah, that's how a pH meter works, right, by the way, is you use, you may have noticed like that has a glass part that allows H+ to absorb in from the outer cell. And you have a platinum electrode, like a little wire dangling down. And you have a cavity for it to store the H2 up above. Yeah, SHEs are very similar to pH meters. They really are kind of pH meters. Yeah, pH meters just have some calibration equipment with them. Yeah, very similar. So this is the redox reaction for the left half cell. This one is for the right half cell. They're different voltages, so your voltage would still pass through them. We put these values into our Nernst equation for room temperature. We can then solve for the H+ concentration, which is the only term we don't know out of these. And that gives us this H+ concentration right here. We can then evaluate the equilibrium constant for our acid-base reaction that has come to the equilibrium in the left-hand cell. Remember, an equilibrium for an acid-base reaction would be a Ka. So it's Ka equals products of reactants. We plug those numbers in, and that gives us our Ka. Notice we just got your book values. Hey, what do you know? Now we can do it. Survival tips. What time is it? Oh, is it? Okay, let's stop here, and we'll pick up here next time. I am going slow. Yeah.